Hello everyone, and welcome to my lightning talk. Today I'll be sharing with you some of my work on lens space surgeries, lattices, and the Poincare homology sphere. To get ourselves oriented, let's take a look at an interesting surgery. Looking at the diagram on the left here, if I do surgery only along the black components, I get the Poincare homology sphere. I can then think of this red component, F, as a knot sitting inside of the Poincare homology sphere. Zooming out on the diagram as a whole, I can perform a diagrammatic move called a slam dunk Kirby calculus and get the diagram on the right. Now, by a theorem in Kirby calculus, these two diagrams present the same three manifold. The diagram on the right very clearly presents a connected sum of three lens spaces, L21, L32, and L54. So the main theorem: let K be a knot in the Poincare homology sphere, and suppose that K admits a surgery to a connected sum of three or more lens spaces. Then K is isotopic to F. And we'll approach this question, this problem, by appealing to ideas and techniques coming from the study of smooth four-dimensional topology. The question we're asking is, when is P over Q surgery on a knot in P a connected sum of three or more lens spaces? And it turns out, from reasons coming from floor theory and from classical lattice theory and from surface intersection graph techniques, the only way that we can have surgery on a knot that's a connected sum of three or more lens spaces where the knot is not this F is when P over Q is 2G minus 1. We can actually show that 2G minus 1 surgery never yields a connected sum of three or more lens spaces by studying intersection forms of associated smooth four manifolds and interactions with Heegard-Floer homology. Now, the main idea to come out of applying Heegard-Floer homology to these smooth four manifolds that we can build up from the data of a Dane surgery is this idea of a change maker. And here's the setup for this. Suppose you have a collection of n+1 coins. Alternatively, we have a vector in z to the n+1. When can you make exact change from the coins in sigma for any value from 0 up to the total value of the coins? So for example, here we have a satisfactory collection, 1, 1, 2, 4. It's not difficult to show that you can make exact change for every value between 0 and 8. On the other hand, here we have an unsatisfactory collection. You can't make change for 2, for example. So we'll call such a vector that satisfies this condition a change maker. And this gives rise to the notion of a change maker lattice, which is any lattice that's isometric to the orthogonal complement of some change maker sitting inside minus z to the n+1. So this is z to the n+1. But the inner product we have is minus the standard dot product. And we'll be looking at change maker lattices specifically in the context of intersection forms of four manifolds bounded by lens spaces, these canonical four manifolds bounded by lens spaces. If I can write the fraction P over Q according to this continued fraction expansion, then LPQ bounds the four manifold I'll call XPQ, presented by this Kirby diagram. And so I get a lattice embedding obstruction. If 2G minus 1 surgery on a knot in the Poincare sphere is a connected sum of lens spaces, LPIQIs, then the intersection form of the boundary connected sum of the associated XPIQIs is a change maker lattice. And I can derive this result by building a four manifold Z that I obtained by capping off the trace of this surgery that gives me a connected sum of lens spaces with this boundary connected sum of XPIQIs, and then seeing what Heegard-Floer homology has to say about this whole picture. And from here, we can derive the main theorem. Fortunately, we know that change maker lattices have at most two indecomposable orthogonal summands. This boundary connected sum of XPIQIs has exactly n indecomposable summands. So corollary is that if P surgery on a knot is a connected sum of three or more lens spaces, then P is not 2G minus 1. Thank you for your time and enjoy the rest of the talks.